Hi. So first, I like to thank FAN and the other organizers for giving me the opportunity to speak here at this conference. I spent 3 years in Austin as a postdoc working with Allan, and this has really been a fantastic 3 years for me. First of all, because I had the privilege to do physics with Allan, but also I think I got a glimpse of how science and of how science and research should be done. So actually after my postdoc, I went to the industry and I really moved between different fields. And what I've learned is that really across the fields I worked in, most people, especially those people very devoted to the work, think very highly of what they're doing, and I've kind of dismiss other fields as being unimportant or interesting. Oh, I see this require. But I think Allan is really special and unique in that sense that he's interested in everything. Whatever you put in front of him, he's interested. And I think it's not only because he's a nice guy. He's a nice guy, but it's not only because of that, because he has this special eye of looking at a physical problem and seeing something that nobody else has seen. So everything is interesting for him, and this is something that I try to imitate. I can't say I did, but I try to take with me through my career. And when I think what makes people like Allan really drive, it's not. I'm not a psychologist, but I don't think it's a success. I think it's really curiosity. He has like this kind of childish curiosity for everything, and I really admire that. And I want to thank you, Allan, for the opportunity I got to work with you. So as I said, I actually after my postdoc, I went to work in the industry. I hope I don't shock you when I tell you that in the industry, people are not that interested in what electrons are doing in 2 dimensions. So I quickly learned that I have to learn new skills. So the first skill I learned was how to use a scope, which is difficult but doable. And then once I learned that, I actually worked for a couple of years with MRI systems. First, the startup company where we did basically everything from preclinical to clinical to industrial MRI. And then in a company that actually it was a startup company. In a startup company that was bought by Medtronic, which is one of the largest medical devices companies in the world, where we did what's called interventional MRI. So this is MRI that is being used during surgery. We aimed at brain surgery. And then after a couple of years, actually, I left physics altogether, and I went to work on algorithms, applied materials, doing all kinds of actually algorithms. And I've been in the algorithm field actually in a very transformative time. So basically, when I started working on algorithms, it was like similar to theoretical physics. You build a model trying to solve some problem, but slowly, all the algorithms actually turned into deep learning. And it's a very different approach to solving problems. So I'm telling you all of this actually. First of all, because there are students here which maybe won't continue in the academy, so I want to tell you there are interesting stuff to do in the industry as well. And also to tell you that this is my first physics conference in 14 years. So I'm very glad that I got the opportunity to start my new academic career here in Allan celebration. Okay, so what I'll do actually today is I'll go back in time. Pablo put you right at the upfront of research. I'll go actually back in time and tell you how it all started with the twisted angle. So for those of you who are actually very familiar, maybe it will just be a good story. I hope it's a good story. And for those of you who don't, I really will go slowly, and I hope that by the end of the talk you really understand at least the basics of the magic angle story. So it all actually started, this for me, when Guru was actually here, and another student, which I don't remember his name. I tried to find out yesterday, but nobody seems to remember. But history is actually well, it's history. You can say whatever you want. So, but anyway, so they came to my office and asked me to help them with a bonus question. So actually, Allan gave a course in condensed matter theory and in condensed matter, and he asked the students to I don't know the exact question, but to describe how electrons hop between two layers of graphene that are twisted relative to one another. So Guru and the other student came to me, and we tried to figure it out. And when we think about it, it's a question that seems a bit stupid in the beginning. When you start looking at it, because if you look at two graphene sheets that are rotated, it's a big mess. So even if you write, some model from some area on this twisted system, it really tells you nothing about the system, because every place looks very, very different than the other one. So we, it was very difficult to even say what was the question, and we talked about it for maybe half an hour, maybe an hour, and Guru and the other student actually left disappointed, and I was left stuck with the problem, and I thought about it for a couple of hours, and so it was just a bonus question in the course. So after some time, I went to Allan, kind of embarrassed, and told him, you gave them this question. What is the solution? What's the answer? So he told me, I have no idea. And and that's really how we started working on this problem. And but what Allan did tell me, that he had some experimental results. I don't remember what was the source. That when two layers are rotated with respect to one another, they act as independent graphene layers. There's no hopping, and that's actually very surprising, because the distance is just 3.4 angstroms, very, very small. So why don't they talk to one another? So this is really the problem we started working on. And the first thing we looked at was actually the tunneling current, right? So think about it, that you take two graphene sheets and you rotate them relative to one another, and then you put some bias voltage between the top and the bottom layer. Okay, and the question you ask is, what is the tunneling current? So what is the tunneling current is a function of this twist angle. So what we used is this very well-known tunneling Hamiltonian that was, I think, mentioned already in a few talks by Emmanuel Tutuk and also by others, I think. So this is a very well-known expression, which is basically gives you the tunneling current. It's second order in the tunneling, so it's perturbative in the tunneling, but it's not non-perturbative in the bias voltage. Right, so usually what you do in this kind of tunneling experiments, you take this T out. You say it's just take it as a certain energy scale, and you take it out. This is what done usually in Josephson junctions and other tunneling experiments. But what we actually did is we looked at the momentum resolved tunneling. What we did is simply used a very simple approximation, we call the two-center approximation, that says that the tunneling between two carbon atoms on the two layers is just a function of the distance between them. And when you do that and you calculate the tunneling matrix element between two states, so you think about it, you have a momentum state, crystal momentum state K in one layer with value alpha, and you have another P prime momentum state in the other layer in value beta, and you calculate the tunneling matrix between these two states. Actually, here it's band energies, alpha and beta. Then what you find this expression. So this expression actually has two things that it's worth looking at. Are worth looking at. The first is that you have to conserve crystal momentum. Okay, so if you take a momentum K and add to it a reciprocal lattice vector in one layer, and you take a momentum in the other layer and add reciprocal lattice vector of that layer, they have to be the same. So crystal momentum has to be conserved. So that's the first observation. And the second observation is that this Fourier transform of this tunneling function, it's a very rapidly decaying function of momentum. So really, when you have this large sum, you only care about values for which K plus G1 are small. When it's very large, this number is very, very small. Okay, so we had this expression, and we actually had an expression for the tunneling current. What we also had was actually some understanding of what's commensurability and non-commensurability. This is due to a very, I think, nice paper that by Shellcross et al. That I remember using a lot at that time. That basically looked at two twisted graphene sheets and divided the system into commensurate angles and non-commensurate angles. Okay, so let me just explain to you, for those who don't know, what is I mean by commensurate and non-commensurate. So it turns out that if you twist two graphene sheets, there is an infinite number of angles, zero measure, but infinite number, for which the system is crystalline. So what it means actually is that if you look at, for example, something like this, so you have one carbon atom on top of one carbon atom in one layer, and there is also another place on the system where two carbon atoms sit exactly on top of one another. So if this happens, you have a commensurate angle. The system is actually crystalline with a very, it could be a very large unit cell, but then it's just a crystal. Okay, but if it's angle difference than these commensurate angles, so actually the system is not crystalline. So what Shellcross et al. Did, they basically calculated, they solved this equation. It's kind of what's called the Fourteen equations. It's equations with integer variables that are integers, and they solved for all the commensurate angles. So we already knew all the commensurate angles of this system. And quite generally, you can describe such a system by using this equation. So basically a rotation matrix that rotates one layer with respect to the other, and a translation vector D. Right, it just shifts one layer with respect to the other. And commensurability is only determined by rotation. So once you have a commensurate angle and you shift one layer with respect to the other, all you do is change the unit cell, but the system is still crystalline. Okay, so we knew actually that, and we had an expression for the tunneling current. So what we did is we calculated sorry, the conductance between the two layers. Okay, so what you see here is a logarithm of the conductance as a function of twist angle. So there are, right, when you look at this image, a few things stand out. The first thing is that it's a peak structure. So usually the conductance is very, very small, but there are some twist angles for which suddenly it increases considerably. And the other thing is that really the peaks differ in strength by a considerable amount, because this is a logarithmic scale. So this is really the two questions that we wanted to answer. We got these numerical results, and we wanted to understand what's special about these angles, and why are the strengths of the different peaks different. And what we did immediately realize is that these angles corresponded to the commensurate angles. So we wanted to know what's special about the commensurate angles, that for these angles you get this peak in the conductance. Okay, let me just say in brackets that what we also saw, that our calculation broke down for small angles. So we already saw in this stage that small angles, something different was happening. At this point, we didn't understand what, but we saw that our theory basically broke down at small angles. But we were interested here in this stage, at least at the large angle. So basically, to answer both of these questions, there is one thing you need to realize, and this is basically the symmetry that you have in K-space. So look at this image, this figure. So what you see here is basically the Fermi surfaces of the two layers. So let's say the blue are the Fermi surfaces of the first layer, and the red are the Fermi surfaces of the other layer as a function of Kx and Ky. Okay, so one Fermi surface is rotated with respect to the other. Okay, and these Fermi surfaces are extended over K-space using reciprocal lattice vectors, right? So these are basically equivalent points in K-space. Now the thing to note, after you see these pictures, the important thing to realize is that the symmetry of the Fermi surfaces in K-space is exactly the same symmetry, or very similar symmetry to the carbon atoms in real space. Okay, so whenever you have a commensurate angle, so whenever you have two atoms sitting on top of one another, let's say in the origin, but also in different places, then necessarily you have Fermi surfaces that overlap. So look at, for example, this image. So you have like a Fermi surface of one layer, of the other rotated layer, and they do not overlap. But if you add to them reciprocal lattice vectors, then you have nesting. And because the Fermi surface is circular, you have perfect nesting. So this enables you basically to conserve crystal momentum and energy together. And this is what allows you to tunnel. Okay, so the idea is actually very, very simple, right? Once you have a commensurate angle, you have necessarily two Fermi surfaces that overlap, like you see for this angle, and then you have strong tunneling. And once they do not overlap, you have very weak tunneling because you cannot conserve energy and momentum together. So this is one answer. This is answer to one question. The other question was why do the peak different in strength? And this is because it depends where the nesting happens. So for example, look at these two angles, 21.8 degrees and 27.8 degrees. You see that the nesting here happens at a smaller momentum than here, right? So this point would correspond to this point. It would be closer to the origin than this one. And as we saw before, the tunneling current or conductance is proportional to the Fourier transform of the tunneling function, right? It's a very fast decaying function of momentum. So this conductance, right, will be actually larger than the, yeah, so you see here, for example, that this conductance for 22 degrees will be larger than for 28 degrees, right? Because the nesting in momentum space happens at a smaller momentum. Okay, so basically we understood what's happened. So this basically explains the experimental results. When you have large twist angles, usually the systems are decoupled, except for some commensurate angles for which you can really tunnel. And this was actually observed experimentally using very recently, maybe even before actually. I'm not very, very updated, so if I'm not stating an important result, I apologize. But I saw this result actually in the quantum twisting microscope that Pablo described in the previous lecture. So this, like Pablo explained, this is a microscope. Oops. This is a microscope that actually allows you to study tunneling between two graphene sheets by putting one graphene sheet on a substrate and the other graphene sheet on the tip. So what Barrett did from Shachal Ilani's group, they measured the conductance, and what they saw is that you have really these peaks at exactly at these commensurate angles that are predicted by theory. You get these large peaks. Okay, so this basically kind of closed the story for us for large angles, but then we realized that something different is happening for small angles. And we actually, I think the small angles really has one concept that you need to understand this, what happens in small angles, and this is the K lattice. So I'll try to now explain this concept for small angles. Okay, so before that, let me again reiterate on something I already said. So if you look at small, we now focus on small angles, and again, we look at this tunneling function. And as I told you before, there are two things here to notice. One is a conservation of crystal momentum, and the other thing is that this tunneling function is a function that decays very, very rapidly with momentum, right? Because the distance between the layers, you cannot resolve anything on a distance which is smaller than the distance between the two layers. Yeah. So these are the two main ingredients that you need, and when you realize these two effects, you basically see that this infinite sum of reciprocal lattice vectors, this exact expression for the tunneling can be replaced by only three terms. So these are the terms for which crystal momentum is conserved, and K plus G1 is small, the smallest possible. So for example, here you see one example. So what you have here is K Dirac plus P prime equals to K Dirac plus K. So you have conservation of crystal momentum, and this argument is just approximately K Dirac. So this is one process, one tunneling process, which is strong, and there are two additional processes that can be obtained by just rotating this figure by 120 degrees, either clockwise or counterclockwise. So basically, what the results you obtain is the following: that if you have a K state, you can only tunnel to 3 states, or to very good approximation, you only tunnel to 3 states, either to K plus QB, which is this process, or K plus Q top right, or K plus Q top left. So you only have 3 processes for which you can, only 3 processes basically control this tunneling. And this leads basically to, and I think this is the central idea actually of the whole paper, that to this idea. So think now that you are in state K, you can tunnel to, as we just explained, you can tunnel to 3 states, right? To the 3 black dots here that from this red dot here. But once you did, you can now either tunnel back or go to different 2 states, and so forth and so forth. So basically, by only considering these 3 states, what you obtain a K lattice in K space. This means that only out of the infinite number of K states, only an infinite but still much smaller number of K states are coupled. So now if you think of your full Hamiltonian, right? So you can actually block diagonalize it, right? Just each point K now in your new Brillouin zone will couple to these K states. So each block in the Hamiltonian will describe such a K lattice, right? So now all you need to do is basically choose a K state, and this will actually give you the Brillouin zone, right? All the K states that, let's say, lie in one of these hexagonals, shift this K point and get a set of energies. And this is precisely Bloch theorem, sorry. Right, this is exactly Bloch theorem. What it tells you is that you couple different momenta, and for each momenta you get a set of energies. So this is precisely a Bloch theorem, and once we realized that this was Bloch theorem, then it's really very simple, right? You just use the Bloch theorem. Basically, you can describe the system using energy bands, and basically what we understood is that even though the system is mathematically not crystalline, for small angles it doesn't matter. For small angles, it's still meaningful to talk about energy bands even though it's not a crystal, right? And this comes from the fact that when you do this approximation, the Moret potential, which is mathematically not a periodic potential, is actually, to an excellent approximation, behaves like a periodic potential. So I think this is maybe the main idea behind this Moret bands. And so one thing we did is basically to calculate the bands you need to do a numerical calculation. But if you're just interested in the velocity, you can actually do it analytically. So you can just look at a minimal model. So a minimal model, would be just to take one K state and just look at the three nearest neighbors, right? So basically you have like an 8-band model, 8-band again because of the valley. So you have 4 momentum states and times 2 valleys. So you have this kind of minimal Hamiltonian, and this you can solve actually, you can solve for the velocity analytically and obtain this expression, which basically tells you that when you rotate the 2 layers, you still remain with the Dirac-Cohn, but it simply flattens. And this is the expression for the velocity. And what you see is that for certain parameter alpha, which alpha is given by W, which is the tunneling energy between the 2 layers divided by the graphene velocity times K Dirac times theta. So this is the only parameter that was in our theory. When alpha squared is third, you get velocity vanishes. Okay, so you can get basically 0 velocity because of a twist. And if you want the velocity at even smaller angles, then this 8-band model is no longer good. You actually have to take the entire K lattice or a larger K lattice into account. So this has to be done numerically, and then what you see is actually that the velocity oscillates. So it becomes 0, increases again, becomes 0 again, and so forth. Okay, so these are the this is the result for the velocity, but if you want to get the entire band dispersion, you have to do it numerically. So this is what we did, and then you see that again for relatively large angles, you see really the Dirac cone, which is just with a smaller velocity, but at roughly 1.1 degrees, you get a really flattening of the band, and this was actually very surprising, and because we tried to understand it for a while with no success, we called it the magic angle, simply because we couldn't understand it, and this right. And then as the velocity, as the twist angle further reduces, you get the band to be more dispersive. So this actually was also recently measured experimentally, again using the tunneling microscope, the quantum twisting microscope, right? So what Barrett et al. From Shachar Ilani's group were able to see is to measure the band dispersion, and basically sees that at 2.7 degrees, the dispersion matches the model. Okay, I just want to mention one thing which actually we also wrote in the paper, and I think wasn't, to the best of my knowledge, wasn't tried experimentally. It's a very simple thing, and people did such complicated things with this twisted bilayer, so I just want to mention it. So you know, you can think about when we so you can think about two configurations, right? One is just the one we described before, where you have a tunneling between the two layers, and you put some bias voltage and current flows from one layer to the other layer. But you can also think about counterflow conductivity, right? Where you basically bias each layer separately, and you drive current in the opposite directions. And then actually, I think you can expect something very interesting. So what we thought about is that if you look at the conductivity, right? Conductivity usually has like a V squared term, right? One V coming from what you measure, and the other one from doing first order perturbation theory, and you have density of states. Now, what happens in typical for typical conductivities is that this density of states in graphene goes like 1 over V squared. So basically, this velocity cancels, and the conductivity is independent of the velocity. But if you look at counterflow conductivity, so what you can show is that this velocity for the density of states actually goes to 0, but the counterflow velocity is not going to 0. So what you can expect, I think, if you do counterflow measurements very close to the magic angle, again, you probably want to be away from the correlated state, so maybe at a large enough temperature, you should be able to see a very large counter flow conductivity, maybe some interesting state around that area. I think actually this wasn't studied to the best of my knowledge. Okay, so I know I couldn't resist looking at, and I tried to look for what the reviews we got on the paper. So I couldn't find it actually. It was probably in an email, but what I was able to find is what we wrote back to the editor and to the reviewers. So there was some sentences that we used from the review, so I just copied them. So I think it's interesting to see maybe in a perspective of 14 years. So we got so we first submitted the paper to Nature Physics, and it was rejected. And this was the main comments that we got. One comment was that the work is too simple. That the numerical work that uses lots of plane waves needs to be scrutinized. The other thing we got was that unfortunately the current manuscript does not add any new information to the problem. And the final was that the results are likely wrong. So yeah, so I think it's interesting to look back and see how, yeah. So, okay, so maybe the last thing I want to say, and this I'll just say, just in passing, again, I won't go into details, that the last work I did with Allan, actually, the first thing we thought about after that was what happens in the magnetic field, right? That's maybe the first thing to think about. So it is known that right, when you put an electron in a magnetic field and you add a crystal potential, so when you put it just in a magnetic field, you get the Landau levels, but when you add a crystal potential, you get what's called the Hofstadter butterfly, right? This very nice fractal structure of energy bands. And what we realized is that right here we have a system that, and usually this structure, right? We all learn about lambda levels in quantum mechanics courses of condensed matter, but we don't learn about Hofstadter butterflies. That's because these are usually not accessed in the lab. You need very, very large magnetic fields to see them, because you need basically the two lengths of the problem, the magnetic length and the crystal length to be more or less the same. This is when you have an atomic crystal, you need the magnetic lengths to be of order of angstroms. That's not achievable in the lab. But here we have actually a system with a very large periodicity. So we expected to see a kind of this structure, and we calculated it, and I saw that actually many experiments see this behavior, and I think it's commonly seen today. You see all these Hall conductivities that change share numbers very rapidly. So this is maybe the last thing that we did. Okay, so I would like to maybe summarize very simply and say that I think really this work is a series of very, very simple questions. I think also with very simple answers. So it's it's worth maybe asking the simple questions. I think that that really engineering new materials is a very good path for seeing novel physics. And the last conclusion is maybe that bad reviews for good physics is actually a good sign. It's a great sign. So thank you for your attention.